And now chapter 3. Finally, we start with a chapter on numerical methods, which is the aim of this course. And after viewing some fundamentals, some background on electromagnetics theorems, now you have a strong background, and we can build your knowledge on how to solve the equations of electromagnetism numerically to obtain a solution for analysis of practical things like antennas, scatterers, anything. Okay, so very briefly in the first part we will do just very briefly some fundamentals that are just to give you an overall picture, and then we will start with the most important part of this chapter, which is this. First, the formulation of integral equation methods. You already know from chapter 2 the surface and volume integral equations derived from equivalence theorem, but they have their advantages and disadvantages, and we will analyze the properties of the different equations and see what are these equations useful for. And now, very important, the discretization of these equations. We will discretize these equations by the method of moments, also called the method of weighted residuals. And it is a method that can be used to discretize any kind of linear equation involving functions, but we will use it here for integral equations, which is the main application. The result is a linear system of equations, and then we will dedicate some time to the different methods for the solution of the linear system. After a few examples of commercial software and also something about Nystrom method, which is an alternative method to method of moments, we will see very briefly something about fast solvers. Well, we could dedicate a complete course or more than one course to fast solvers, and here I will just introduce why it is possible to solve a huge system of equations that huge system of equations means, for example, a system of equations having up to 1,000 million unknowns, that is 1 billion unknowns, 10 to 9 unknowns. In it is possible to solve it, and of course you cannot do this using conventional solver. You need these fast solvers that take profit of the properties of the linear system, the properties of the integral equations that after its discretization led to the linear system. So these properties are the ones that allow a fast solution. Okay, but we could dedicate many hours to this. In fact, it is our own field of research, but we will just give you an overview about how is it possible to obtain a solution with a computer of a huge system that would be otherwise impossible to solve, and what are the fundamentals, the basis of the different available methods. And then we will dedicate a short time to other methods, not integral equation methods based on finite differences, and this I will not dedicate much time to any of this, but just give you an overview of the fundamentals of the method and the advantages and disadvantages of all the methods, so that you can choose which method is better for a particular application. All these methods are used in commercial software. You will use commercial software not only in electromagnetic applications like the pictures in this slide, but if you for sure you will work on some field of physics or engineering, and for sure you, at any time in your working life, you will use numerical simulation software, commercial software. It's very expensive. It is often very expensive, often tens of thousands of euros, the license, but also very powerful. You can see here some examples. This is an iPhone 4. When I did the slide, it was the very latest phone in the market, but now it's quite obsolete. But anyway, we discretize the geometry of the phone, especially the geometry of the metallic or conducting parts of the phone, also if they are relevant, also dielectrics if necessary. And then the solution of the linear system of equations that is built by the simulation software. The solution of the linear system of equations is the current J. J is the current, the surface current or induced current at the conducting surfaces at every point in the phone, or the equivalent current in case of the electric object, it would be the equivalent currents. But anyway, the solution of the numerical of the linear system that is built by the software is the current, and this plot shows the current magnitude at different parts of the structure of the phone. For example, red color is the strongest current intensity, and it is located at near the feeding of the antenna. Blue color, dark blue, is the lowest intensity of current, and in the meanwhile we have, after blue color, the next is green, yellow, orange, and then red. Okay, and dark red would be the strongest magnitude of current. So you can see, in fact, that the current excited by the feeding of the antenna extends on the whole structure of the phone, not only the antenna itself, but also the chassis, the ground planes, and all the printed board of the phone, everywhere. And it is the whole structure of the phone that behaves as an antenna. So the antenna is not only the antenna itself, but the antenna is everything within the phone. And this is what is analyzed by the numerical. So you have to discretize everything and analyze the whole phone altogether. And after obtaining the currents, you use the conventional equations for the radiation of currents in free space. Remember surface equivalence theorem, or also volume equivalence, that equivalent currents radiate in free space. And if you obtain the induced current, remember that the induced current is equal to the equivalent current, and the equivalent current, and therefore the induced current, radiate in free space. In the equivalent problem, in the original problem, remember that the induced current does not radiate in the original problem, but in the equivalent problem, the induced current equal to the equivalent current radiates in free space. So from the radiation of this current, we obtain the radiation pattern. And it is easily done by the usual integral that we, at the end of chapter 1, we derive the integral that allows us to compute the electric and magnetic field due to some electric current, and by duality also magnetic current. But we can compute not only the radiated field, but also the induced field. So this should be the field close to the phone, that is the induced field. The radiation pattern, you usually compute a pattern for every observation angle, and here you compute the field at all points in the volume of space surrounding the phone. Okay? This is also interesting. For example, if you want to compute the behavior of the phone when it is close to a human head, the user of the phone, we have to compute the radiation pattern of the phone, taking into account the epsilon and mu. Mu is non-magnetic, okay? Mu approximately equal to mu 0, non-magnetic, but the dielectric constant is obviously different than epsilon 0 because the human head is a dielectric medium, and this modifies a little bit the radiation pattern of the phone, but we can also compute the near field inside the head to check if it agrees with the regulations about the power, that the electromagnetic power that can be the maximum allowed electromagnetic power that can be dissipated inside the head. Okay, so for the example, for this phone, they have computed that in 1 gram of human brain you dissipate 1.68 milliwatts, which is according to which agrees the norm, the regulations. We can compute anything. This is, for example, the reflection coefficient at the input of the antenna versus frequency. So we can see here the resonant frequency, the frequency at which the antenna behaves better. You see that these are GSM band frequencies. But for example, when we change the epsilon of the cover of the phone, of the plastic cover of the phone, you can see that there is a shift in the resonant frequency of the antenna, and so the antenna does not work so well. So okay, this is just an example of what can be done with commercial software. You will be users of commercial software for numerical simulation, maybe not in the electromagnetics, maybe in other fields of engineering or physics, but this anyway, even if you work in another field, this course, although it is focused on electromagnetics, will give you some insight on how numerical simulation software works in general. This is just an example. This is in this chip we have here an antenna. We have an antenna here. This is an antenna. We have a feeding of the antenna here. This is an HF antenna. The wavelength is of several meters. So the antenna can be, the wavelength can be up to 30 meters. So the antenna is usually smaller than the wavelength. It's a small antenna, but the whole structure of the chip behaves as an antenna. So you can see the induced current everywhere in the metallic or conducting surface of the chip, and the whole chip radiates as the antenna. Okay, and you have to analyze everything all together here. And you can see here an example. This is not in fact a numerical method. This is ray tracing, RT. Ray tracing, we have an incident ray here. It reflects, or perhaps this one. Here it reflects, here, 2 reflections, 3 reflections. 1 reflection here, then it goes down, another reflection here, it goes back, another reflection here, and back to the incident radar. This is an aircraft. Imagine that there is a radar here, this is a radar, and the radar produces a field that hits the target, is scattered by the target, the echo, and the scattered field goes back to the radar, and the radar measures the scatter field and determines that there is that it detects a target. So it is very important to compute the magnitude of the echo, of the radar echo, the magnitude of the fields scattered from the target back to the radar. This is called the this is done thanks to a parameter called RCS. We will see a lot about RCS in chapter 4 in this course, next chapter, about scattering and high frequency techniques. In fact, this ray tracing is a high frequency technique because it computes the scattering of radio waves as rays, and rays is light are rays. So we assume that the object is much larger than the wavelength, and that radio frequency waves behave as light, and so they form rays. This is an approximation, but it's very interesting because then we don't need to solve a linear system of equations like we did here. Here we had to solve for this shape a very large system of equations, and here for the iPhone we also had to solve a very large system of equations. So using these high frequency approximations like ray tracing, we don't need to solve a system of equations, and the computation time is much shorter. So we will dedicate to chapter 4 to this kind of methods, and chapter 3 to this other kind of methods involving the solution that build, that discretize the integral equations, build a linear system of equations, solve it by some fast solver, and then compute the induced current on the surface of the target. Normally, these high frequency methods here in chapter 4, they directly compute the field scattered back to the radar or scattered everywhere in any direction. They usually compute the field, the approximate methods in chapter 4. However, in chapter 3, the solution of the linear system of equations is the current. And from the current, we integrate the current, the convolution of the current with the Green's function, and then compute the radiated field or the induced field. So, how can do this? Well, this is just a flow chart, a flow diagram to show you what we do with integral equations. We have the equation here. This is the electric field integral equation. Electric field integral equation. And remember that we obtained this equation at the end of chapter 2 when we were working explaining surface equivalence theorem, and we derived surface integral equations, and one of them was the electric field integral equation, this one. And here we have an integral equation with a impulse response, a convolution with an impulse response that is the Green's function, and very importantly, this Green's function is singular. The denominator becomes 0 when r equal to r prime. The Green's function is infinite, okay? It is singular. And since it is singular, this integral is difficult to compute. It's an improper integral, and we may need to do something. We need to do some analytic integration of the singularity or whatever, or use some very accurate numerical integration. But this singularity of the Green's function will be always a problem, always an issue to solve in integral equation methods. Okay? So, we have some equations, in our case the integral equations. We discretize it. We will use method of moments that we will explain in a video later in this chapter. We discretize the integral equation with method of moments and obtain a linear system of equations. This system of equations often has millions of unknowns. Why? Because we have to discretize the surface of the target. Here we have a horn, a typical horn antenna, okay? Typical horn antenna. We discretize the surface, and after solving the system of equations, we obtain the current in the surface of the antenna, okay? But in order to do that, we need to discretize the surface of the antenna. This is the antenna here, sorry. Well, it's very bad, this drawing. This is the surface of the antenna. It has been discretized into thousands or tens of thousands or maybe hundreds of thousands of small triangles that model the surface. Why triangles? Because with triangles you can also discretize easily curved surfaces like, for example, a sphere, okay? So, you discretize the surface, but you need that your discretization cells be much smaller than the wavelength. The size delta of these triangles must be much smaller than the wavelength. And for that reason, if the object is much larger than the wavelength, the size of the object is much larger than the wavelength, and the size of the triangles is much smaller than the wavelength, you need thousands, tens of thousands, hundreds of thousands of triangles. And at the end, the solutions, the unknown, are the current on each triangle. The current on each triangle has two components. So in principle, we need two unknowns, one for each component of the current, per triangle. Since there are some continuity relations, etc., we can simplify, and in fact we don't have 2 unknowns per triangle. We have less than that, we have 1.5. But anyway, the idea is that the number of unknowns in the linear system, so then the number of current unknowns, of the unknowns for the vectorial current that we have to compute, is of the same order of magnitude as the number of triangles. So we have thousands of triangles, then we have thousands of unknowns. And the linear system has many unknowns. The order of the linear system very often is 10 to 5, 10 to 6, up to 10 to 9 in the largest cases that has been solved with integral equations. So in order to solve such a large linear system, we need a fast solver. We need a fast solver, and this will allow us to solve this. I will more about this later, but it is possible. It is incredible, but it is possible to solve a linear system with 1 billion unknowns in a computer. In this case, a supercomputer, but we can solve 10 to 8. We can solve 10 to 8 in a normal computer. Okay, and the solution of the linear system is the current. And when we have the current, here remember that the unknowns are related to the components, to the surface, the vector component of the current. Once we have the current, we can compute all antenna parameters. We can integrate the convolution of the current with the Green's function and obtain the radiation pattern. We can, once we have the radiated field, we can compute the input impedance. We can compute everything. For example, in this case, I will have a plot here of the radiation pattern. And as I told you, we have to discretize the surface into many small triangles. You can see an example here. This is a car. Remember what I told you, that the size of the triangle must be much smaller than the wavelength. The size of the car is much larger than the wavelength, so we need thousands of triangles in one dimension, hundreds of triangles, or maybe thousands of triangles again in the other dimension, and if you multiply this, you end up with millions of triangles, and that's the problem. Okay. So once you have the current, you remember that you compute the current for each triangle. Normally, the two components you get the two components of the current, the vector components of the current for each triangle. And here we have a plot of the current magnitude and the car surface. We have a plot also of the induced field here, and we have a plot also of the radiated field. This has been obtained by commercial software, but you see here that one of the key and very important things is to obtain the mesh, the triangular surface mesh of the model. You will you remember that in this course you will do some practical projects, and in one of them, in practical project 1, you will do several things, but one of it will be to create a three-dimensional mesh of triangles to model a hyperbolic surface, a curved surface, and you will learn how to manage and how to write the computer code to manage the mesh, the triangle mesh, and to do calculations, computer calculations with the triangle mesh. And now about the types of numerical methods in electromagnetics. There are two main divisions. In the first division, you can consider time domain methods or frequency domain methods. In time domain methods, you solve the integral or the differential equations in time domain, that is, as a function of time. You can solve either Maxwell's equation or the wave equation, like in this example, or integral equations, everything in time domain. So you have 4 variables, the 3 variables of space usually Cartesian x, y, z, and also the time. So you have 4 variables in your discretization, and all your functions depend on these 4 variables. On the other hand, you also have frequency domain methods. Frequency domain methods, you assume harmonic regime, that is the time harmonic variation using phasors. The phasors, like this scalar potential here, depend only on space, so they depend on the 3 variables of space, x, y, z, and not in time, because you replace, in the fact it's like in a Fourier transform where you replace the time variable by the frequency variable. You work in the Fourier domain, you work in frequency domain, and your variable is omega, the frequency, but you keep omega, the frequency, fixed. So now you have in fact 4 variables, the 3 variables of space plus a frequency, but the frequency is fixed and it's no longer a variable. So in fact your equation now it has 3 variables that are the space variable, and the frequency is a constant. The frequency is a constant, a constant parameter. And what happens if you need a wideband solution? For example, imagine here the first slide. Here you have the reflection coefficient and the input and the feeding port, the input of the antenna of that iPhone 4. You have the reflection coefficient S11 as a function of frequency from 0.6 gigahertz to 1.3 gigahertz. How can you obtain this frequency response? Well, very simple. If you use a frequency domain method, which is it's quite common, what you do is you have to solve many times the problem for different frequencies. So you define a vector of frequencies, and for each frequency you obtain, you can see here, the different frequency samples. So for each frequency you have to solve again the problem. This is quite time consuming, because if you define, for example, 200 frequencies, you have to solve the problem by numerical simulation 200 times, 1 per each frequency. But you can also obtain a time domain solution as a function of time. For example, here you would obtain the S11 coefficient as a function of time. Then you do a Fourier transform and obtain the S11 parameter as a function of frequency in the Fourier domain, in the frequency domain. So you can also use a time domain method, obtain the solution as a function of time, Fourier transform, and then the solution as a function of frequency. This is often better when you need a wide band with many frequency samples. It is very often faster to obtain the solution in time domain and do a Fourier transform to obtain then the solution in frequency domain for many frequency samples. It is usually faster than solving the frequency domain problem hundreds of times per each frequency sample. Okay? We can also do a second division. The first division was time domain methods or frequency domain methods. But we can do a second division. Finite difference methods or integral equation methods. In finite difference methods, you approximate, you start with equations that are based on derivatives. Equations having no integrals. Equations having only differential operators. Differential operators are the derivative, a second derivative that is the Laplacian, or vector operators, first order operators like gradient, divergence, curl, second order like Laplacian, operators involving only differences, not integral operators involving, for example, convolutions. Okay, only differences in differential operators. Examples of these equations are Maxwell's equations, only have curls and divergence, or wave equation that only have Laplacians. Okay, they are operators having only equations having only differential operators. In this case, we can approximate the derivatives that are implicit in these operators using finite difference. Remember from your mathematics courses that you can approximate a derivative by just a subtraction of the sample of the function samples that are very and 2 points that are very close, and divide by the separation of these samples. This would be a first order derivative, like here. If we use central differences, we have, for example, if we compute the derivative, here, we must subtract one sample at the right minus one sample at the left, and divide by the separation between these samples. And since these samples are at this from the left sample to the right sample, the distance is 2 spacings. If one spacing is delta, the 2 spacings are 2 delta. Okay, delta in this case, if this is x-axis, would be delta x. So for that reason, I have 2 delta x here. Okay, this would be an approximation of the derivative at the center sample using central differences and using finite differences. The smaller the separation between samples, ideally delta x is very, very small, close to 0. The smaller the separation between samples, the more accurate the approximation of the derivative with finite differences. Okay? Of course, this can be applied only to methods that have only differential operators, like Maxwell equations and wave equations. Very popular example is FDTD. More about this later in this chapter. We will dedicate a lesson to or a video to this FDTD method. But it's very commonly used in electromagnetics. It is time domain method. It stands for FDTD. FDTD stands for finite differences, so this is a finite difference method in time domain. FDTD, finite difference time domain. It is very commonly used method in electromagnetics, because it was in fact one of the first methods, because it's quite easy to write a program, so a computer program, so late in the 1960s, maybe 1966, if I remember it right, about 1966, it was the first code to analyze electromagnetic problem in 3 dimensions using finite difference in time domain, because it's quite easy to discretize my Maxwell equations in that way. Very important, this kind of methods, finite difference methods, need a 3-dimensional volume discretization. 3-dimensional if we are in frequency domain. In time domain, you need an additional dimension for time, so it is 4 dimensions. But regarding space, you need a 3-dimensional discretization. Why? Because your equation, for example, this wave equation here, your equation is defined in a volume. R belongs to the volume where you do the analysis. In volume V, you do the analysis in volume V. So you have points R at all the points R at all the points within volume V. So your equation is defined in a volume. Your variable, the potential here, is defined in a volume, or in case of Maxwell's equations, the electric and magnetic field are defined in a volume. So you need a volume discretization mesh. So you have to discretize a space like here. So if you remember the slides they put there, you do remember the slides like that slide or that one in which you discretize the surface with a surface mesh. In this case, for finite difference methods, you cannot use discretization of the surface in triangles. You have to discretize the full volume. Look at these elements. These small elements are volumetric elements, like this. This is a volumetric element. Imagine a cube, for example, cubes, tetrahedrals, or parallelepipeds that have 3 dimensions. So you have to discretize the volume in 3-dimensional small elements like this, not like a surface. Well, let's draw it better. Not like a surface in small triangles. You need 3-dimensional discretization elements like cubes, tetrahedrals, also very commonly used tetrahedrals, okay? Whatever, non-cubic parallelepipeds like this, whatever, but volumetric elements, okay? You also need a truncation boundary condition to finish the space. But more about this later. I will explain when we dedicate a video to finite difference methods. I will explain what is the truncation boundary condition, but you need one of these. Another example of a method that is widely used apart from FDTD is the finite element method. This method is probably the most commonly used numerical method in engineering in general, not in electromagnetics. In electromagnetics, the most commonly used methods are this FDTD method that I mentioned before and method of moments that I will explain later. But in engineering in general, finite element methods probably is the most commonly used. It is very common in civil engineering to modeling structures, in fluid dynamics, in thermal modeling, in physics, and of course it can also be applied in electromagnetics, and since it is a finite difference method, then I include it in this slide. All these finite element methods are based on the approximation of derivative with finite differences, so they relate. Observe here that these methods relate. All these methods relate only samples that are close together. For example, if I have to discretize the difference equation, the Maxwell's equations or wave equation into finite difference, at last I get a linear system of equations, and this linear system of equations relates samples of the unknown, samples of the unknown function. And observe that these relations are only between samples that are close together. This minus this, okay? And this minus this. You only relate samples that are close together, but you do not relate this sample here with this sample here. You don't relate these two. So I cross this out. You don't relate these two. So I cross this relation, okay? Because they are not neighbor. So they are not subtracted one minus the other in the finite difference approximation. And this means that the matrix that includes the relation between all the samples between all of them, there are many zeros because almost all pairs of samples are unrelated. Only a few pairs are related one to the other, okay? So in the linear system where you get the relations between the samples, almost all the relations are zero. Only a few of them are not zero. So you get what's called a sparse matrix. Very important. And you can also model inhomogeneous media, because in your equations, your parameters, remember that this here you have, this is k, okay, square, which is omega, k square is omega square mu epsilon, okay? And here, these constitutive parameters can depend on space. You can have propagation constant k that depends on space, or mu epsilon depending on space. So this can be inhomogeneous because at every point you put the value of k that is according to the epsilon and mu of that point in space, okay? So the medium can be inhomogeneous. And it is also very important. So there are two important points, sparse matrix and inhomogeneous, and can be applied to inhomogeneous media. Well, the other kind of numerical methods that are, apart from finite difference methods, are integral equation methods. Integral equation methods are derived from a surface equivalence formulation of the problem. Then you analyze the equivalent problem, you set the boundary condition for the electric or the magnetic field, and you get the electric field integral equation or the magnetic field integral equation. Okay, I have presented already these equations at the end of chapter 2, and an example of this is in one of the previous slides here. Here you have an example of the electric field integral equation for perfectly conducting surfaces. That is, it is based on a surface equivalence formulation, and analyzing the equivalent problem, you set the boundary condition for the electric field, and you get this. And the unknown is J. The unknown is J, and J, remember that this is the induced current, but in fact, in the surface equivalence formulation, it is the electric equivalent current that we have seen that for PEF in chapter 2, we have seen that for PEC, perfectly conducting objects, the equivalent electric current is equal to the induced current. For that reason, I have put the induced current in the equation, but in fact, it's the equivalent current. And very importantly, the equivalent current is defined only on the surface of the object, not within the volume of the object. So this convolution integral, the sources are in the boundary of the object, in the surface of the object. This is volume V, normally the outside, so the unknowns are defined on the surface of okay? So if the unknown is defined on the surface, you only need a surface discretization like this. Here you discretize only the surface of the horn, and here you discretize only the surface of the car. Okay? And this is very important. So a very distinctive feature of the integral equation methods is that the unknown is defined on the object surface, so you only need a surface mesh, not a volume mesh like in finite difference methods. You only need a surface mesh. And of course, the surface mesh is usually divided in small triangles or small quadrilaterals, not necessarily rectangular, okay? Can be trapezoidal. But you need much less unknowns, much less discretization elements in a surface than in the full volume, okay? However, now you don't have a finite difference discretization of the operators. You have a convolution integral. And this is very important because for a convolution integral, to compute the field at every point, you have to sum the contributions of all the source points R prime. So there is a full relation between points R and R prime. All points R need the summation of all points R prime. So all the points of the object surface are related with all the points of the object surface, not like in finite difference methods in which you only have relation between neighbor points. Now you have relation between all the points with all the points. So the linear system that you get has a full matrix, a matrix in which all the elements are different than zero, okay? And also very important, remember that when we explain surface equivalence, I said that you need an homogeneous medium inside the volume where you applied surface equivalence. So where in the volume B, where you compute, this is surface S, in the volume B, where you compute the fields, you need that the volume B must be homogeneous. This is very important because remember that in finite difference method, the volume could be inhomogeneous. So if we want to summarize all the differences between integral and differential equation methods, we have that regarding the discretization, differential equation methods need volume discretization, while integral equation methods need surface discretization. This means that the number of unknowns n, we usually call n, the number n is the number of unknowns. If n is the number of unknowns, then we have here n large for differential equation methods and n small for integral equation methods. Now, regarding the linear system matrix, with differential equation methods, we have obtained a sparse matrix that includes many zeros, and it's very efficient to solve this because you can solve the linear system. You have a matrix, the linear system has a matrix n times n by n, okay? The linear system is like this, and you have a matrix of order n in the linear system, so you can solve the linear system matrix in n to 1.5 operations, which is in fact very fast. However, integral equations methods need a full produce or lead to a full linear system that has no zeros, so you need n to 3 power operations to solve the linear system. If you use a direct solution like, for example, Gauss or elimination method or LU decomposition or whatever, and if you use iterative method, you need the number of iterations, which is k times n squared, but the number of iterations grows with n, so you go close to n to 3 operations to solve the linear system. So it is much faster to solve a linear system, a sparse linear system, than a full linear system. So there is a balance. Differential equation methods need and produce a linear system with n large, but then you can solve the system with a small power of n operations. And in integral equation you get a smaller n because you have only surface discretization, but the power of n is larger, n to 3 or n to, let's say, 2.5 operations to solve it. So in this case, no, it's not clear if it is better to use a differential equation method or an integral equation method. In fact, normally it's better to use an integral equation method with surface discretization. However, for very large objects, we can use fast solver. Remember that I mentioned before that we have fast solvers that allow the solution of iterative methods not in kn squared, but in kn log n. K is the number of iterations. Number of iterations. And usually k is, let's say, something like of order n to 0.5, for example. So here the order gets n 1.5 log n. Okay? So it becomes comparable for large n. It becomes comparable to n.5. In fact, it is n.1.6 or like that for sparse matrices. So the power of the power of n in the order of the number of operations that you need to solve the linear system, if you use a fast solver, becomes comparable between integral equation methods and finite difference methods. But however, with integral equation methods you have surface discretization, and n is much smaller. For that reason, you can solve very large objects with integral equation methods and surface discretization when you use a fast solver that allows you to solve up to 10 to 9 unknowns in a supercomputer. And this is the method of choice for solving very large problems. Integral equations with surface discretization, fast solver, and very big computer. And this is a nice example. This has been done by the group of computational electromagnetics at the Universitat de Extremadura and in cooperation with Universitat de Vigo. In fact, this group have joint researchers between the two universities. And these are the induced currents on a car, a Citroën car, at 79 gigahertz. So the wavelength is about, let's say, about 3 millimeters or so. The wavelength is very small. And the number of unknowns is 600 million. It is not the biggest example. It was the biggest example that I have for a practical object like a car. But for canonical objects like spheres, or this object here, this is a well-known benchmark, it has been possible to solve 1.5 billion unknowns, which is presently, as far as I know, the world record. It has been computed in a supercomputer with 1,000 processors and 4 terabytes of RAM memory. So, to summarize, what are the solution steps? Well, first, as I said before, you have to do a formulation of the problem that you have to solve. It can be in time domain or in frequency domain, or it can be a differential equation, or it can be integral equations. Okay, but you start with some formulation of the differential and internal equation. It must be, of course, a linear operator. Now you have to discretize all these equations that can be differential or integral into a linear system. The linear system, there are many methods of discretization. The two main ones are the method of moments, that we will dedicate a video after this to method of moments, and the finite element method, and there will be another video dedicated to this method by the end of the chapter. So just first formulate your equations, and second discretize this equation into a linear system. But you also have to discretize the boundary conditions, because you have to discretize the surface in the case that you use, for example, surface integral equations. You have to discretize the surface, for example, into a mesh of triangles. And this mesh of triangles is approximate, because if, for example, this is a sphere, what you get is a polyhedral having many faces that is close to the sphere, but is not exactly equal to the sphere. So you also you have to discretize the sphere, and you introduce error in this discretization. But you also have to discretize not only the surface, but the boundary condition at the surface, because you set the boundary condition with functions. You said tangent component of electric field equal to 0. Well, this is a function of the electric field, and you have to convert this into numbers. So you, for example, can set the boundary condition to a sample, that is a number, of the electric field at the center of the triangle, or you may set the boundary condition as that you can compute for example, the minimum. You can compute the square error of the boundary condition average, the square error inside the triangle, that is a number. The average square error inside the triangle in the boundary condition is a number, and then you set this number into the linear system. So you have to discretize the boundary conditions that are equations into numbers, but whatever methods. Samples, average, minimum, minimum square error, or whatever, okay? But you also, in the case of differential equation methods, you also have to set mesh truncation conditions in the linear system. More about this later. I don't want to dedicate time to this here, but you must be aware that when you set the boundary, when you discretize the differential equations into finite differences, and you make the subtraction of one sample at the right with minus one sample at the left, if you want to compute the approximation in that point here, you need one sample at the right minus one sample at the left. So you need one sample more. And when you compute the approximation here, you need one sample at the right minus one sample at the left. And you need infinite samples in an infinite volume. Of course, you cannot do that. So you have to terminate, you have to do a mesh termination somewhere to convert the volume into a finite volume. And you need what's called a mesh truncation condition here, that is a differential equation that is valid on the boundary. It's a differential equation that only needs samples of the field inside the boundary but not outside the boundary. So you have to do this, more about this later again, but just you must know that it is something else that you have to do apart from the discretization of your equations and the discretization of the boundary conditions and the surfaces or the volumes. You also have, in the case of finite difference methods, you also have to set these mesh truncation conditions. And this is important because they introduce error. In fact, all the steps that we have seen in this slide, all of them introduce error. First of all, even the equations that we have formulated, even Maxwell's equations, wave equations, integral equations, whatever, all the equations introduce simplifications and approximations, because the real life problem, the problem that we have to solve, is much more complex that we can model with equations. The equations are just a simplification of a very, very complex problem. For example, you know that the object may be not perfectly homogeneous. There can be uncertainties in the knowledge of the constitutive parameters epsilon and mu. There may be the shape of the object cannot be exactly spherical or whatever. There may be errors we don't know exactly the shape of the object. There may be also other effects that we don't take into account, also multiphysics effects, etc. So there are always approximations in the statement of the problem. So we just build a simplified model, and also, as I said before, the material parameters epsilon and mu are we cannot know them exactly, and we know them just approximate values or possible values, but not the exact, mathematically exact values are impossible. Okay. Of course, the discretization introduces errors. Errors into building a linear system. A linear system has order n, so the original functions are in a functional space of infinite dimensions. Our linear system has order n, so it has n dimensions. So we discretize, we reduce a problem of infinite dimensions into a problem of n dimensions. So this introduces error. Okay. Also, we have to compute integrals, the convolution integrals. And the numerical computation of integrals introduces error. And if the functions have singularities, of course, they are much more difficult to integrate, and the error may be larger. As I said before, we also have to approximate finite difference by derivatives. So derivatives are approximated by finite differences, and also this also introduces error. You have to approximate the surfaces with meshes, or the volume with a volume mesh. This introduces error. For example, remember the spherical surface here. The spherical surface was discretized into a mesh of triangle. The mesh of triangles is a polyhedral not exactly equal to the sphere. We have to discretize the boundary conditions into numbers, I said before. Either a sample or an average of the error of the boundary condition, average of the square error, whatever. This also introduces error. The truncation boundary conditions that I explained or introduced here, that will be explained later, also introduce error. But so we have errors in the formulation, errors in setting the linear system, but also when solving the linear system, we have errors because in the linear system matrix we have numbers. And numbers are, computer numbers are finite length number, often with, in double precision, 64 bits numbers, and in single precision 32-bit numbers, but these numbers use finite length words that are just approximations of the real numbers. And this it seems that approximating a real number with a finite 64-bit double precision computer number that has a relative error in this approximation 10 to minus 16, it seems that it's extremely good approximation, but sometimes when the linear system is poorly conditioned, and more about this later, sometimes this effectively introduces errors in the solution. And it's important to know about this and to take this into account. We also very often use iterative methods to solve the linear system instead of direct methods. Iterative methods are often much faster, but the iterative solution converges to the exact solution after n steps if n is the order of the matrix. But we often, if n is 1 million, we don't want to make 1 million iterations. We want to make 100 iterations. So we stop the iteration when the error in the linear system residual is small enough, often a relative error of 10 to minus 2, 10 to minus 3. So this also introduces an error because we don't stop the iteration when we have achieved convergence to the exact solution, I mean the solution of the direct system, of the direct solver, but we stop the iteration as soon as possible in order to save computation time. This introduces error. And also, when the system is very, very large and we use a fast solver, fast solvers always involve approximations. So we always introduce error with fast solvers. So there are many, many, many sources of error. So many, there are so many things that go wrong, and I made a joke here, that it is almost magic that it works. It's very difficult to have everything working in a real life system. So when you buy computer software, a full software package for numerical solution of an electromagnetic problem, and this costs you 50,000 euros, I repeat, 50,000 euros, a lot of money. It is because that it was extremely difficult to have a software package able to handle any problem that, or almost any problem that you can imagine and set it into the software. It has so many different modules able to solve so many different problems with so many different methods, taking into account so many different approximations. And it's so many years of work, so many people, maybe 30. For example, I have in mind a computer software. They told me they have 30 postdoc, that is 30 engineers or physics having a PhD done on the topic of computational of electromagnetics, 30 postgraduate PhD scientists working in formulation and in the algorithms, plus the programmers, plus so many people, so many effort. It's very, very difficult. There are so many things that can go wrong, so it's very, very, very difficult to have everything working. Of course, in the practical projects that we will do, you will do here, it will be very easy because we will choose for you the simplest problems with the simplest algorithms algorithms and the simplest everything, so that the overall will be easy and manageable for you. Of course, you will not find that easy. You will have to work hard, but I can assure that what we propose for the practical project will be easy compared of the difficulty of what we have in real life problems. So here I repeat my joke, it's almost magic that it works. And just an example to show you how difficult it is. This is a very difficult example. It has been chosen as something very difficult to analyze, and of course it has been they have used commercial software. Of course the commercial software is correctly programmed. Everything is correct there. There are no errors from well, of course there are discretization errors, etc. But what I mean that everything is correct in the software. Okay. So the difficulty is for the user to accurately do the mesh of the object, the mesh here of the, this is a GSM antenna, like the antenna in a mobile phone, but it is in a printed board, but it's a similar antenna to that of a cell phone. And you have, of course, to discretize the antenna into triangles, etc. And the difficulties are in doing the triangle discretization and choosing the parameters of the triangle discretization, and also in setting the parameters of the simulation, because of course there are many parameters to choose in the simulation. And it's difficult. So the difficulty now it's on the side of the user of the software. The software is correct. So the difficulty is on the side of the user. And the users here were students, normally graduate students, most of them PhD students, working at different research groups, and they use different commercial software like this: Magmas, IE3D, Momentum, FECO, CST, HFSS, CST again, Empire. All these are different different softwares or numerical modeling softwares. Okay, and compare with measurement, which is the black dash line. This is the input reflection coefficient S11 and the feeding port of the antenna, which is this here, S11 here. Okay, and versus frequency. And what you get with different software is different. Only two of the solutions are more or less close to the other, that are these CST solutions here, this and this. The two CST solutions obtained by two different groups are more or less not very different one to the other, but the rest are completely different, and again all of them are different from the measurement. So this just shows that it's difficult to make a correct computation, and the software of course is okay. There is no problem with the software. The problem is with the user that does not know how to properly model this antenna using the software. Of course, this example is very difficult. There are many examples that are easy, and you just solve everything. You just set all parameters at default values, and you get a perfectly correct solution. Okay, there are many easy examples. Like for example, a half wavelength dipole. It's an easy example. You can solve this with any software and obtain a very nice solution. Okay, but here a difficult example was chosen, and you observe that all the results were wrong. So the same example, the next year, the same example was proposed to the software vendors, the companies that produce the software. Of course, they were very interested in obtaining the correct solution, because otherwise it will be bad for the software propaganda. They will be a very bad advertisement of the software if they don't get the correct solution. So they did a very important effort in setting the correct simulation parameters. So they did set the correct simulation parameters, and again the same software, but now used by the software vendors, got the correct result. Okay, and this is the measurement. Of course, if you compare the two very accurately, the two curves, you will see that the resonant frequencies are not exactly the computed resonant frequencies that now are the, remember antennas, you get, when the antenna is resonant in real input impedance with no imaginary part, you get the minimum reflection coefficient because you get the best match with the feeding transmission line, so you get the minimum of the reflection coefficient at the input. So at resonance is when the resonant frequency is where you want to use the antenna. And you will see that the resonant frequencies computed by the software are not exactly the same as measured. And this is because this problem is also very difficult to model. This model did not account for the currents in the coaxial feeding line. The coaxial feeding line had also some currents at the exterior of the outer conductor that must be taken into account. So this is a case when you introduce the error in the approximations when you write the equations. When you write the equations and you set the model, here you neglect the currents and the outer conductor of the coaxial feeding line. Okay? You don't model this. You only model this. And you don't model this. So this is an approximation. And this approximation produces the miscomputation of the resonant frequencies that are not exactly equal as the ones that are measured. And this is important. It's just an example of how difficult it is to compute, to obtain, as a result of the computations, to obtain the same as in a measurement. Because first you have to properly use the software, setting the correct value for the parameters, and second, your model has to be the model of what you are measuring, okay? Because sometimes what you model is not exactly the same as what you measure. And all this is very important and must be taken into account. With all this, we finish with the introduction, and now we will start with the first analyzing in detail the first kind of method, that is integral equation methods, that we will dedicate most of this chapter to integral equation methods and only shorter videos at the end to finite difference or differential equation methods.